Yo, peep the style and the way the cops sweat us. The number one question is, can the feds get us? I got vendettas and dice games against ass betters and niggas who...
Okay, so this is something a little bit new. Parametrizing circles. Okay, so for a circle, let's say we have a circle of radius r, and I'll use a capital R, radius r, centered at origin. At the origin. So in this case, like I said, we're just working in 2D right now. So the origin would be 0, 0. Okay, so let's say our circle is something like this. Hey, I'm getting better at that. Okay. Yeah, so we're here, and our parameterization is actually going to look like x, our x coordinate. So here's our x and our y. Our x coordinate is based on the parameter theta. We're going to use theta for our parameter, okay? And y is our sine theta, okay? So basically, like I said, this theta is our parameter. So this circle crosses at r, and then negative r, right? It has radius of r all the way around, centered at the origin, 0, 0. And so when theta, let's say we're here, so here's theta, then this point here on the circle, that would depend on our angle, and you would calculate that by using r cosine theta for the x variable, for the x coordinate, and r sine theta for the y coordinate. Okay, so then as we go around, so theta is going to go from, let's see, we start at 0, let's say, okay, so 0, and an angle of 0 would be pointing in this direction, so that means we're at this point, the one I'm highlighting here, okay? And then as theta grows, larger than 0, then it'll move along, so we'll move around the circle like this, right on the curve there. Okay, we're going to keep going, and at this point, when we're pointing in the negative r direction, in the negative x direction, when we're at this point here, that would be when theta equals pi radians, or 180 degrees. Okay, so we're going to keep going along the circle around the bottom, and we come back and complete that circle at 2 pi. Okay, alright, so now a more general parameterization of a circle would be if it were not centered at the origin. So let's say, again, instead it's centered at some point out here, AB. Okay, so we have a circle going on. I really am getting better at that. Okay, don't judge me if it turns out weirdly in future videos. Okay, so we still have radius r, okay, but this time our center is at AB. So the only thing that changes here, we're going to have the same parameterization. So this one's, we'll just say that's kind of in the middle. The theta ranges from 0 to 2 pi, because it's going to be the same for this one. So anyways, x is going to be not only r cosine theta, but we're going to add the a to it. The a from the center, right? Because that's the x coordinate of the center, plus whatever r cosine theta is, okay? And likewise, we're going to do the same with y. We're going to throw in that y coordinate of the center, so that added to it, right? And then plus r sine theta. Okay, so this, the bottom is the more general way of writing it, and if you notice, if your center is at 0, 0, then A is just going to be 0, and B is going to be 0, and we get back to our simple parameterization, where the circle is centered at the origin. Okay? Alright, so now for an ellipse. So what is an ellipse? You've probably seen it in Algebra 2 class, trigonometry before. It's basically like an oval kind of thing, a stretched out circle. Okay, so the parameterization for an ellipse, well, first of all, let's see what it looks like. So this is going to be a little bit more different than, okay, 1, 2, 3, 4. Let me count first so I didn't lose track. 1, 2, 3, 4. Okay, so here's 2, here's 4, and we're going to go around like that. Okay, yeah, this is a little bit tougher than a circle, as you might see. Okay, so that's the general idea of an ellipse. Okay, so the parameterization for our ellipse is actually going to be the following. So we have our x coordinate is defined by a times cosine t, and I changed it back to t because, I don't know, just because I felt like it. You could always put a theta here if you want to. Either way, you can choose whatever parameter variable you'd like. And of course, it's based on the problem too that you get. You should always use the same parameter variable as the problem. So what we have is this, and the equation for an ellipse is usually x squared over a squared plus b, well, no, not b, sorry, y squared over b squared equals 1, I believe. Yeah, so something like that. So as you can see here, this actually works out to be true, or the parameterization makes sense, because when you plug in this for your x value, you get a cosine t squared over a squared plus b sine t squared over b squared equals 1. And so we have an a squared over here. So the a squared, and then we have a cosine squared t over a squared. These cancel. Plus b squared sine squared t over b squared. Those are going to cancel, and you're going to get 1. And that is true from the trigonometric identity that sine squared plus cosine squared equals 1. So the parameterization works. This is just key to remember. It's more or less just you have to remember what it is, what the parameterization is. Anyways, but this just gave you a little bit of background on why it works. Okay, so anyways, so this, what I graphed here, this is our curve c of t, okay? And this actually graphs the specific parameterization of 4 cosine t and 2 sine t. And as you'll see, the a is 4, a equals 4, and b equals 2, right? Okay, so that means that it's actually going to stretch 4 units in the x direction each way. Okay, so this is a negative 4 over here, 4 to the right, 4 to the left. And then on the y-axis, it's going to stretch 2 up and 2 down from the center. Okay, so that was the specific like drawing for that. And then, okay, so that's it for the ellipse. And now we'll go on to a perhaps a new graph that you might not have seen before called a cycloid.
Tried to do me in, I ain't paid them yet. Trying to push 700s, they ain't made them yet. Rolex and bracelets, it's frostbit. Rings too, niggas riding away.